Question 1b of the 2012 Flight B summer exam requires you to apply Newton's second law, in its angular sense. So the sum of moments about the center of gravity is equal to the mass moment of inertia about the y-axis multiplied by the angular acceleration. Then you have to apply small perturbation theory, and from that you can go through, and the idea is to apply that to work out the second order characteristic equation representing the aircraft's longitudinal response. So once we have that, we can go through and we can calculate out the stability derivatives, and we can have a look at, say for example, the static stability of the aircraft and even the longitudinal stability. Okay, so you're given the following, and this part here, so these two equations are your linearization, using small perturbation theory. So what you can do is you can sub in these values into here. Obviously this is the angular acceleration, whereas this is the pitch angle values. So you end up with so that's your reference moment plus the disturbance in the moment. So that could be numerous things which we'll go through in a minute. So the mass moment inertia about the y-axis, reference acceleration, and your displacement angle. So now if we assume that you've been told to assume that m0, your reference moment, is 0. If you don't have a reference moment, then you won't have any acceleration, any reference acceleration to begin with, or angular acceleration. So that simplifies the equation down to delta m is equal to Iy delta, the pitch acceleration. So once you have it down to that value, the next part is you've been told that your disturbance, so the disturbance in terms of the moment, the pitch moment, can be, in its linear sense, any combination of the following terms. So the first three could be due to usually external disturbances. So for example, you might have a gust which ends up changing the aircraft's angle of attack, or the pitch rate. The final one is due to pilot control, so the pilot can also change the elevator deflection, which adds a moment to the total aircraft. So what you can do is you can take this entire equation, you can sub it into the previous equation that you had, and it results in the following differential equation. So one of the hints you've been given is that your coefficients can be rewritten in a more compact form. So for example, you can write mq as dm, so the change in moment over the pitch rate divided by the mass moment of inertia. So if you apply this, so you can end up, if you divide both sides by Iy, you can get the rest of these terms in more compact form. And then your differential equation ends up looking a little bit more like this. So m alpha delta alpha, so that's your change of moment with respect to the change in angle of attack, multiplied by the change in angle of attack due to the disturbance, and similar sort of thing with the rest of the terms. Okay, another assumption that they've given you in there is to assume that the body fixed and the fixed frame are aligned to each other. So what that means is normally your pitch angle relates to, it runs through the fuselage reference line, so your pitch angle changes as the aircraft rotates, but your angle of attack is related more to your wing. So if you align your wing and your aircraft so that your angle of attack, if your angle of attack equals 0, that your pitch angle equals 0. So and you continue the same relationship all the way through, having the same alignment, you could say that your angle of attack and your pitch angle were aligned together and that they were the same. So then if you apply that back to your previous equation, which was you could have the following relationships to simplify this further down. So you could, for example, if alpha dot is equal to that, then you could say, well, if angle of attack is equal to pitch angle, you could say the rate for the angle of attack change is equal to the pitch rate change, which is also equal to, so you could say, for example, your delta Q and that way these two would line up and they could be combined together. In a similar sense, your theta double dot could become an alpha double dot because they're essentially the same terms now. So if you apply the following two relationships, your differential equation simplifies down to now in terms of inputs and outputs, as you'd have with most differential equations, you can put the inputs usually on the right hand side, outputs on the left hand side. So if you rearrange that, you would get so this ends up forming a relationship between, so if you had an angle elevated deflection of a certain, in terms of, this would be calculated in radians based on the equation, you'd get a particular angle of attack relationship out for the system. Now for the second part, you've been given a that equation, so it's fairly straightforward. On the second page, you go through all the values. So it's fairly straightforward. As long as you plug all the values in and you stay consistent with all the terms, you'll get the values out. So that's shown in the solution set you can have a look at. So I'm not going to go through the calculations, but in this case you get MQ is equal to negative 2.405, M alpha dot is equal to negative 0.819, M alpha is equal to negative 2.823, and M delta E is equal to negative 7.11. So in terms of static stability, normally we have a look at the coefficient of moment, which is in its linearized sense referred to as the following, and if your Cm alpha term is negative, it indicates that you've got static stability. Now here you don't have Cm alpha, you've got M alpha, but M alpha is equal to Cm alpha Q, so dynamic pressure, wing planform area, and your root chord. So the thing is, all three of these values are going to be positive. So if you've got a negative M alpha value, you'll also get a negative Cm alpha value. So from your M alpha value, you should be able to tell. So for this aircraft, you can tell it's got static stability, but you don't have a Cm naught value. So from this, you won't be able to tell whether or not the aircraft is trimmed for a positive angle of attack. The other thing you can also work out from this is, now that you've got all the values, your characteristic equation, or your differential equation, can be written out in the following way. So from this here, you can go on and you can do further things. You can apply a Laplace transform to this, you can get the transfer function, and then you can apply, say, some sort of value in for your elevator deflection. So I think the calculations are in radians.